Hey, what's up? How many infinities even are there? Well, I'll tell you right now, it's more than 5. So let's start with B0. So I'm going to call a collection of things a set of elements. So B0 is going to be the set of elements 0, 1, 2, 3, going on forever. I'm going to call those the natural numbers for this video. So B0 is an infinite set. It has all the natural numbers in it. How can we get a bigger infinite set? Well, let's think about it. So here I have the set containing 1, 2, and 3. So a subset of this set is a set that I can make out of the elements. I can build it out of the elements in this set. So I could include or not 1 in my subset, that's 2 choices. I could include or exclude 2, that's 2 choices. And I could include or exclude 3, that's 2 choices. For a total of 2 times 2 times 2 possible choices. So here's all my subsets that I could form. Here's the empty set where I excluded 1, 2, and 3. Here's a subset where I included 1, 2, and 3. And here's a subset where I included 2 and 3, but excluded 1. So I have 3 elements here, and I have 2 to the power 3 possible subsets. So what can I do with all of these subsets? Well, I could form a power set. So here S is the set 1, 2, 3, and the power set of S is the set of all subsets of S. So because S is 3 elements, the power set of S is 8 elements. So what I can do is I can take the power set of B0 to get B1. So if this is like the size of the set of natural numbers, this is like the size of the set of real numbers. But why did I do this? Why power set? Why not just add an element to this set? Isn't that good enough to get a bigger infinite set? Well, let's think about it. So here I have the set 1, 2, 3, dot, 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 and here I have the set 0, 1, 2, 3, dot, dot, dot. So in some sense, this set is bigger than this set, right? Because look at it. This set has all of the elements in it that this set does, plus an extra element. We would call this a proper superset of this set. So in that sense, yeah, it's a bigger set. But in another sense, they actually have the same size because I can put the 2 sets in a 1-to-1 correspondence with each other. So in that sense, we say the 2 sets have equal cardinality. So you see, when we take the power set of a set, we're guaranteeing ourselves a greater cardinality. So this is a bigger infinite set in a really meaningful sense. These 2 can't be put into a 1-to-1 correspondence. So now what can we do? Well, we can take the power set of this set to get B2. This is like the size of the set of all functions from the reals to the reals, and not just the continuous ones. And then we can take the power set of this set to get B3. This is like the size of the set of all topologies on the reals. And we can keep going on like this forever and ever, taking more power sets. So is that it? Is that the end of the story? Well, no. There's a way we can make a set that goes beyond all of these in cardinality. So what we're going to do is we're going to take all of these sets and we're going to combine all of their elements into one big single set. We'll call that B sub omega. This is a really big infinity, but we can go further, right? Because we can take the power set of it. I'll call that B omega plus 1. We can take the power set of that. I'll call that B omega plus 2. And then this goes on forever and ever, taking more power sets. What can we do to get a bigger set? Is that the end? No. We can take all of these sets and combine all of their elements together to get B sub omega times 2. And then in a similar way, we could continue on forever with power sets, combine all of those together to get b sub omega times 3. And now notice the pattern, omega times 2, omega times 3, omega times 4, omega times 5. We could get up to b sub omega squared. And with enough work, we could even get up to b sub omega to the omega to the omega, going on forever. Okay, what's going on with these omegas? So formally, we're assuming ZFC axioms, which are the standard axioms for almost all of modern mathematics in this time period. So omega and b naught are formally going to be both the same set. This is the set of natural numbers. Omega is the set of natural numbers. In this case, I use the omegas to think of them as ordinal numbers. They kind of measure the order of things, so to speak. And the b's are to measure the size of things, so to speak. So these I think of as cardinal numbers. These I think of as ordinal numbers. Don't worry about it too much. The point is, here I have b sub omega. I like to think of this as the infinitieth Beth number, where by infinitieth Beth number, I mean infinity as in the smallest infinity. So here I have the infinity plus 1th Beth number, the infinity plus 2th Beth number, all the way up to here. So what is this thing? It's hard to even explain how big this thing is. Let me just try to explain to you how big this thing is. So first, we take all the power sets of B0 repeatedly. Then we combine all of those together. Then we get this. And then we take all of its power sets repeatedly, combine all of those together to get this. And then we take all of its power sets together, combine them all together to get this. Take all of its power sets, combine them all together to get b omega times 4, and then do the same thing, and then do the same thing, and then do the same thing, going on forever. And we take all of those and combine all their elements together to get b omega squared. We haven't even gotten up to b omega cubed, and definitely not this thing. But the question is, how many Beth numbers do we have so far? How many? Well, only B0 number of Beth numbers so far, actually. Because you see, the thing is, omega to the omega to the omega going on forever with ordinal exponentiation is actually the same cardinality as B0. So we just have B0 Beth numbers so far. And by the way, what are these Beth numbers? Well, they are infinite sets that we use to measure the size of certain other infinite sets. But there are actually possibly more infinite cardinals than just the Beth numbers. The standard axioms don't settle that question, but for our purposes, the Beth numbers are going to be good enough for what we're trying to do here. So the question is, how can we get more Beth numbers? Well, why not? Since so far we have only gotten B0 number of Beth numbers so far, how about we just go skip ahead in line all the way up to the b sub 1th Beth number. So now, going from here all the way up to here, we have b1 total number of Beth numbers. And then we could, if we wanted to, go up to the b sub 2th Beth number. Now we have up to here b sub 2 number of Beth numbers. Another way we could get further is we could just do b sub b sub b sub 0. So b sub 0 is just b sub 0. B sub 0 is just b sub omega. So b sub omega is what this one is, which is going to be bigger than this, because see, here we have the b first Beth number, here we have the b second Beth number, and here we have the b omega-ith Beth number, and b omega comes further along than these two do. So this is a bigger infinity. By the way, this is a crazy big infinity, but guess what? Why don't we just do this? Right? Why not? Do you see what I'm doing right now? I think you know what I'm doing right now. Just go b sub b sub b sub b, going on forever. Why not? That's a Beth number. We'll call it z. So z is a really, really big infinity. It's hard to even fathom how big it is. But now, it is time to stop fooling around and ask the ultimate question. Because, you see, with z here, we can go further. we can just take the power set of z to get an even bigger infinity. So it just goes on and on and on. So let's just think of this as a grand, wild list of all of the Beth numbers that there are. All of the Beth numbers. The question is, how many Beth numbers are there? Which Beth number measures the infinity-ness of all of the Beth numbers, or surpasses the infinity-ness of all of the Beth numbers? So are there B sub 0 Beth numbers? Well, no, there's more than that. Are there B sub 1 number of Beth numbers? Well, no, there's more than that. Maybe Z number of Beth numbers total? No. There are more Beth numbers than any Beth number can measure. The number of Beth numbers is beyond infinity, or at least that's the way I would like to say it. But to be fair, it is infinite, right? Because it's not finite. So, but it's an infinity that transcends and stuff. An infinity that is properly in a class of its own, if you will. It's what you would call absolute infinity. And that is where I'm going to end the video. If you have any questions, including technical questions, feel free to ask them. And yeah, just think about how crazy this is. There are more sizes of infinity than can be measured by the size of any one of those infinities. Thanks for watching, and goodbye.